Okay, welcome to lecture 5. So far we have been introducing a range of applications of multi-agent system. We'll see multi-agent system can be applied to solve a number of classical artificial intelligence problems. And one of the things in common with a number of the problems that I just showed you was the employment of an economic paradigm. And this is quite natural because a multi-agent system consists of autonomous agents who are assumed to be rational decision makers. Game theory actually plays a very important part in the development of multi-agent systems, and one can argue that the game theory is a very suitable model of all of the multi-agent system scenarios that we're looking at. So from this lecture, we're going to systematically look at some basic notions and models in game theory. So decision-making is a crucial ability of an agent. Decision-making performed everywhere. For example, an automated car needs to decide on the direction and velocity of traveling. A chatbot needs to decide on what to say next. A bidding agent needs to decide on whether or how much to bid in an online bidding. So decision making is really a crucial ability. And formally, we can define a decision problem as consisting of several components. So first of all, the agents involved in decision making will have a set of actions to choose from. So that represent all the alternative form which the player can choose. The set of outcomes are the possible consequences that can result from any of these actions. And then preferences describe how the agent ranks the set of possible outcomes. And of course, this can be different from agents to agent. And also, one of the easiest way to represent a preference is using what we call a payoff function. It's a function that maps the outcomes to real values, so that if an agent think of one outcome as better than another outcome, then the payoff for that first outcome will be no less than the payoff of the second outcome. Right. So we have typically, if we want to define a decision problem, we need to specify these three things, right, in a mathematical way. Right. And one other thing, like what I've said, that we always assume that the agents are rational and they make decisions solely based on their own interest. We can capture this by the notion of rationality. An agent facing a decision problem with a certain payoff function is rational if they choose an action whose outcome maximizes the expected payoff. Right? Notice that the payoff is not necessarily just in terms of monetary reward. It can be a combination of many factors. Right? But the agent is rational if it's always aiming to maximize its own payoff. So in a multi-agent system, the outcome of an action of an agent does not just depend on the agent itself, but also depend on the action of other agents, because we have multiple agents in the same environment. And we also assume that all the agents are strategic, so they will guess what other agents would do and then act correspondingly. Right? So before we present any of the formal definition of games, let's look at an example. Suppose you are faced with two tasks which are due tomorrow. There is an exam which you have to prepare, and there's a presentation. But the thing is, the exam, of course, you take it by yourself, but the presentation is done with a partner. Right? So you have two persons working as a team to complete the presentation. And because you have only very limited time, you have to make a decision on whether to prepare for the exam tonight or prepare for the presentation. Right? Of course, if you prepare for the exam, you'll get a higher mark in the exam. but potentially this will impact your presentation. Right? Similarly, if you prepare for the presentation, then you cannot prepare for the exam, and so you get a very low mark in the exam, but potentially you'll get a high mark for the presentation, right? So you have to balance these two decisions. And we cannot make a decision if we do not describe the details of the payoff functions. First of all, the exam and the presentation are each worth 50% of the final mark, so they have the same weighting. And if you prepare for the exam, then you would definitely, so out of all the calculation, you can be relatively sure that you get at least 92 in the exam, and you will get 80 if you do not prepare for the exam, right? And for the presentation, this will be more interesting because it's a joint work. So the result of the presentation will depend on the action of both of you and your teammate. If both of you prepare for it, then you're relatively confident that you will get full mark for the presentation, so 100. But if only one of the person prepares for it, then there's a key component in the presentation that's not very well designed, and therefore you get 92. So which is quite good, but it's not as good as both of you are preparing for it. But if no one prepares for it, then you just do some really bad presentation. So at the end, you will both get 84. Right. So now the question is, should you choose to prepare for the exam or work on the presentation if you can only do one thing? Right. We can model this game in a mathematical way. And I'm going to describe the mathematical model. And in fact, this is a very simple situation and can be modeled by what we call a static game. Right? A static game involves a number of agents who choose once and for all actions, which in turn cause an outcome. So in that example, you can see that we have two agents, you and your partner, and you only need to make once and for all action, whether to prepare for the exam or for the presentation tonight. And that's the only thing that you're concerned about at this stage. And you'll get an outcome in the next day, right? So in this way, it satisfies the condition of static game. So in this condition, we assume that there are two steps that will happen. First of all, each player will simultaneously and independently chooses an action. Notice that they don't have to choose the action at the same time. As long as they are not aware of the other person's choice before they make their own choice. So this is what I really mean by simultaneously. It doesn't mean that they're making the choices at the same time. So it's just they're seen to be simultaneously making these choices. And the step 2 is that conditioning on the player's choices, there will be some payoffs that are distributed to each player, right? And a static game has complete information if the agents know everything that has been happening. Of course, the agent would not know the other agent's decisions before making his own decision, but he would know everything else. That includes all of the payoff function of everybody, all the actions, what sort of outcome will be the result of what combination of actions. So that's what we mean by complete information. The scenario that I described to you assumes that the agent will have complete information. So mathematically, we can define this normal form game as a tuple n as f. N is a set of players or agents, and S is a set of action, sets of actions. So basically, it specifies the set of actions for every player. So S is formally S1, S2 up to Sn, where Si is a set of actions. We also call these actions pure strategies here, right? And F, again, also would be a set of payoff functions, where we have a function fi for every agent, right? And every payoff function is, notice that the payoff function does not only depend on the action of the ice player, but rather it depends on the combination of actions of all the players, right? So fi will be a function that maps from the Cartesian product of the action spaces of all the agents to a reward, right? Of course, this reward is a reward that's given to the ice agent, but it depends on the collective actions of all the agents, right? And just fix on some terminology. If you have fix a tuple of actions taken from the player's action space, then that tuple is called a pure strategy profile. Right. And if we fix any agent I, and we look at the combination, the set of all the possible action combinations of the opponents. So these are the players 1, 2, 3 up to I minus 1, and then I plus 1 up to n. So that's everybody excluding I. That can be denoted by, in this course, a SI with a overline above it. Right. In the literature, a lot of the books in game theory literature denote this by S with a subscript of negative I, right? But I'm using this notation here. And if we have any tuple of actions of all of these opponents, that can be written as SI with a bar on top, right? So just being consistent with the last notation. And therefore, we can somehow abuse the notation to write FI, SI, SI hat, SI overline, for the payoff FI of all of the actions from S1 to Sn, right? This is just for notational simplicity. So that's the formal model of games that we are working with. And now we can model the previous example using this normal form game. And the best way, if you have a normal form game with say 2 players and each player has finitely many actions, then the best way to represent this game will be a matrix. Right, so this will be a game matrix of the game, and you can see that every entry of the matrix consists of 2 values, because that should tell the payoff to both of the players. Right, so if both of you prepare for presentation, remember in this case, you will not get a high mark for the exam. You'll get only 80 in the exam. But both of you will get 100 in the presentation. And because the exam and the presentation each worth 50% of the marks, so in average you get 90, right? Overall you get 90. And this is when both of you are preparing for the presentation. So now in this matrix, you can see that I'm using the rows to indicate the action of the one of the players, namely you. And I'm using the columns to indicate the possible actions of the opponent, namely your partner. Right. By calling your partner an opponent, it doesn't mean that you are competing. It's just saying that you're both participating in this game. So, for example, if you choose to prepare for the presentation and your partner chooses to prepare for the exam, then you're in an interesting situation because you actually did all the work for the presentation to improve the mark of the presentation, while your partner is being a bit selfish because he's free writing your preparation of the presentation to get 92 in the presentation, but at the same time he prepares for the exam, so he will get 92 in the exam, so altogether he'll get 92 as overall grade, but you only get 86 because of the fact that you did not prepare for the exam. So in this case, you have been taken advantage of by your partner. If you switch the roles, so if you prepare for the exam, your partner prepare for the presentation, you got exactly the same situation, but just switching the roles. So you are taking advantage of your partner. And then lastly, if both of you prepare for the exam, not the presentation, then both of you would get 92 in the exam, but you do quite badly in the presentation. Right. And overall, you'll get 88 each as the overall mark. So this actually is the worst outcome, because if you think about the situation where you both prepare for the presentation, actually in this case, both of you would get better than if you both prepare for exam. So now the question is, what would you choose? Should you choose to prepare for exam, or should you choose to prepare for presentation? Also, this really depend on what you expect your partner would choose. Should your partner choose exam or presentation? So really, you can see that the problem now becomes the following. We've defined this situation which involve agents making choices, and under the condition of complete knowledge, we have everything, right? So the agents know all the setup. And now the question is, we want to predict the outcome of the game. In game theoretical language, we would like to identify a solution concept, right? So what is a solution concept? It's a formal rule that governs how we predict the outcome of a game. A solution concept is determined by the behavior and beliefs of the players. A solution concept specifies a set of game outcomes. Any of these outcomes is called a equilibrium. A solution concept may contain none, a single, or several possible equilibria. Right? So we would, of course, desire a good solution concept that has a certain predictive power that reasonably well capture the agent's behavior. So I want to introduce the simplest solution concept, namely what we call a dominant strategy equilibrium. Right. So the notion of strategic dominance is very fundamental for normal form games. Suppose we have this normal form game with n players, and we pick a player I and two strategies S and S prime from player I's action set. Then we say that S dominates S prime for this player I if no matter what the opponents do, so remember this overline SI indicates the possible action of the opponents, and then overline small case SI is an actual combination of actions of the opponents. So no matter what the other people have done, if you fix the other people's actions, then what the ice player get from playing S would be no less than the payoff that this player gets from playing S prime. And if we add the word strictly in front of dominates, this is even a stronger notion. It says that no matter what the other opponents do, what you get from S is strictly better than what you get from any of the other strategies that you can choose. Right? So a strictly dominant strategy for player I is a strategy S that strictly dominates all other strategies. Right? So suppose there is such a strictly dominant strategy, what do you think the agent would do? Right? As a rational agent, as a rational autonomous agent who do not care about the utility of other agents, then the most reasonable choice would be just to play the strictly dominant strategy. Right? So, in fact, this is the basic assumption that we can make. A rational player will never play a dominated strategy, because that's always going to be worse than the other strategy. A rational player will always play a strictly dominant strategy if there is one. Right? And this leads to the definition of the equilibrium right? Because everybody would, if they have a dominant strategy, they would, of course, play it. And so a strategy profile is a strict dominant strategy equilibrium, or SDSE. If this strategy SI is a strict dominant strategy for all the players. So this is a situation where everybody plays a strict dominant strategy, and that is what we call the SDSE. If you look at that situation where you and your partner are choosing between to prepare for the presentation or the exam, how would you respond? Right? It doesn't really matter what your partner does. If you think about the situation, preparing for the presentation is always worse than preparing for the exam, because if your partner chooses presentation, so you only need to look at the first column, and you only need to look at the first number in each entry, because the first number is the reward that you will get. Right? And preparing for the exam, you get 92 overall, but preparing for the presentation, you only get 90. So obviously, you want to prepare for the exam. On the other hand, if your partner chooses to play exam, again, 88 is bigger than 86, so you will also choose to prepare for the exam. Right? So this is actually, if you think about the real life situation, you prepare for the exam in the fear of being taken advantage of by your partner, right? Because there's a uncertainty about the action of your partner, and there's a possibility that your partner will take advantage of you. So in order to play the safe action of always getting the biggest benefit, regardless of what your partner does, you would just end up choosing to prepare the exam. So, but exactly the same situation will happen to your partner. So suppose that your partner is perfectly rational and self-centered, then your partner will also play exam. So overall, both of you will play exam, which end up at this scenario. Like what I said, this is not a very good scenario, because both of you can get a higher mark if you prepare for the presentation, but you will still want to play at this strategy profile, right? So this demonstrates a very crucial fact in this normal form game. If we recall the optimization problems from the last two lectures, where we talk about the assignment problem and the scheduling problem, we've defined the notion of competitive equilibrium, which is the state where the individuals involved in that decision-making process are making the locally optimal choices for themselves, and yet the overall outcome is optimal for everybody. However, in this situation, the individuals, if they're adopting the action which is the best from their point of view, the overall outcome will not as good as some of the other outcomes. Okay, so they will not be able to reach a globally optimal outcome. Okay, so that's sort of the interesting observation that we can make from this example. Also, one of the things is, if the game has a strict dominant strategy equilibrium, then that equilibrium is unique. So if there is one, then that's the only outcome that we want to predict. So we regard as DSE as the collective outcome of rational choices of agent if it exists. If we look at this next example, we have athletes, athlete 1 and athlete 2, they are in this competitive sport, but they have the option of taking drugs or not. Of course, if they do not take drugs, if both of them do not take drugs, then they will compete in a fair way, and they will get actually good rewards. However, if one doesn't take drugs and the other take drugs, then the other player will have an unfair advantage. As a result, suppose that the physical ability of the athlete are sort of comparable, but this person with this unfair advantage becomes really likely to win the game and getting a very high reward. However, the other player will not completely lose, so you get one reward because out of the health benefits from not taking the drug. So this means that if both of the players use drugs, they will also compete in a fair way, but this will create a negative impact to the health condition of the athlete. So they will not get as high payoff as if both of them do not use drugs. So this is really similar to the situation of preparing for exam and presentation. And we can actually use the same analysis and see that there's only one outcome of this game, which is both players will use drugs. Even though they are fully aware of the situation, they're fully aware that the fact that if they both do not use drugs is beneficial, they will still use drugs out of the fear that they will be taken advantage of by the other player. Right? So that's the analysis that we can get from such situation. And then this brings to the notion of Pareto Optimality. Right? So a strategy profile, Pareto dominates another strategy profile if for every player, we know that the first strategy profile, S, would always give a payoff that's no worse than the second strategy, S prime. Right? And also that we know that for some of the player, this is strict. This relation is strict. So for some of the players, strictly better, and for all the other player is not worse. So this means that it's possible to go from S prime to S, and in this way to improve the condition of some of the players while not damaging the reward of the other player. Right. So in this case, we say that S prime is Pareto dominated by S, and the strategy profile is Pareto optimal if it's not Pareto dominated. Right. So if you consider this last situation, this 2-2, so this condition where both players choose to use drugs, will be dominated by the situation where both players chooses not to take drugs. Right? So an outcome is seen as socially undesirable if it's Pareto dominated. So for example, in this situation where they both use drugs, because it's Pareto dominated, it's not a socially desirable outcome. So it's socially undesirable. Therefore, a good policy is one that allows the agent to coordinate a Pareto optimal outcome. Apparently, under our assumption that the player would choose the strictly dominating strategy, that would not lead to a Pareto optimal solution. Right? So SDSE does not guarantee social desirability. Right? For example, dominant strategy lead to only pure strategy profile that is not Pareto optimal in the previous example. That's the only pure strategy profile that's not Pareto optimal. Also, one of the other problems with SDSE is that there are some cases when we do not see an SDSE. Right? For example, if you have this game, you see that neither of the player will have a strictly dominant strategy. For player 1, for example, if he plays, if the player 2 plays L, then U is the best choice. But if player 2 chooses C, then D is the best choice. Right? And for R, U again is the best choice. So now you can see that no strategy of player 1 is dominating the other strategies, and similarly for player 2 as well. So in this case, if you use SDSE, you would not get any answer. So you still cannot predict the outcome of this game, but we still need to would like to make some prediction. Right? So consider this game. Even though there is no strict dominant strategy for any player, there are indeed strategies that are dominated. For example, the second, for example, if you look at the second, for example, if you look at the option of the second player, the player has an option of L, C, and R, but if the player chooses C, right, and no matter what player 1 chooses, the player 2's payoff will always be less than the player 2's payoff if he chooses R. Right? Because 1 is less than 2, 4 is less than 6, and 6 is less than 8. So in this case, we can reasonably be sure that player 2 would not ever choose to play action C. Right? And so actually, in this sense, essentially, action C can be eliminated from consideration. Right? So with this simple observation, we can apply an iterative elimination procedure. Right? If a strategy S is dominated by another strategy S prime for an agent, then agent I, being rational, would never consider to play S. The other agents, knowing that I is rational, will know that I would never choose this action S. So for both players, there is a reason to eliminate the consideration of S. Right? So we can eliminate S. So in this case, this middle column can be eliminated, and this will give us a smaller matrix. And the smaller matrix, according to our assumption of rationality, is equivalent to the original matrix. Right? And then from this game, we can see from the point of view of player 1, if player 1 chooses M, it's dominated by U. Similarly, if the player chooses D, it's also dominated by U. Right? This does not hold in the original game because of the existence of C, but once we take C out, then you can see that M and D are both dominated. And therefore, we can eliminate both of these two strategies from consideration, and we just end up with this game where player 1 has only one option, and player 2 has two options. So in this case, it's very easy to analyze. Player 1 would choose U, and player 2 would choose L. Right? So then we can make a prediction about the outcome of the game in this way. Although this profile is not a strictly dominant strategy profile, it is also reasonable according to the rationality assumption that we made. Right? So this is what we call a iterated elimination equilibrium, or IEE, and it's a result of a procedure. So in fact, an algorithm. This algorithm will initialize the set of actions as the original set of actions for every agent, and then it iteratively check for any action of the agent that's strictly dominated by another action. And if there is a strictly dominated action, then the procedure just eliminated from the current set of possible actions. And this is repeated until you cannot find any strictly dominated strategy. And at the end, what's left, those strategy profiles, are what we call iterated eliminating equilibrium. Right? And because this is the result of a procedure, we can guarantee that IEE will always exist. Right? And also we can relatively easily verify that if a strategy profile is in SDSE, then that strategy profile is an IEE, and it will be actually the unique IEE because that's the only strategy profile that are not eliminated as a result of this procedure. right? So this also gives us a way to identify SDSE. Let's look at this situation when we have two firms and they are faced with two strategies, either to produce low price products or they upscale to produce, a more high quality product. And the question is, does this game has an SDSE or an IEE? In fact, the question is, or the first question has a negative answer, so there's no SDSE. But we can of course find the IEE in this game, right? So according to the description of the payoffs, the matrix is given below, and then you can apply the IEE algorithm to compute the strategy profile in IEE. I'm not going to work through this with you, but you can. You're welcome to try this yourself. But you can see that low price upscale is the only IEE of this game. Yeah, so this means from 1 we choose low price and from 2 we choose upscale. Right. So far we have described two equilibrium that are very fundamental. But one of the problems with IEE is that in certain cases, if you're given a game, you will not be able to eliminate any strategy from the matrix, right? Because no strategy is dominated. And even though we can guarantee that there are IEEs, it may be that the set of all the possible IEEs contains all the possible strategy profiles, and still we have no predictive power with this notion. And in fact, this brings to one of the most classical and widely known solution concept in game theory, namely Nash Equilibrium. Okay. So if you think about the situation when we have multiple players, in fact, from the point of view of every player, they want to play it well from the point of view of themselves. So this means that given the opponent's strategies, the current player will want to optimize its own payoff, right? This is the most reasonable assumption. The action that the player chooses does not need to be dominating other strategies, because domination is a very strong notation. But instead, as long as the player is acting in the best response to the current action of the opponent, then we're saying, well, the player will choose to do that. Right? So this leads to the definition of best response. Suppose we have a static normal form game. We take a strategy and also a couple of opponent's strategies. We say that this strategy S is a best response to the opponent's strategy. If for every other actions that can be taken by this player, this S will give the highest payoff. So Fi of S prime, given the opponent's strategy, will be less or equal to the Fi of S given the same opponent's strategy. So now notice that this is a weaker form of dominance. In the notion of strategic dominance, we require that no matter what the opponent does, we are choosing the strategy which is maximum, which gives us maximum payoff. But here it's just that if we fix the tuple of actions by the opponents, the action S will give us the highest payoff. Right, so that's a much weaker form of strategy dominance. But the solution concept will lead to the equilibrium, which we call Nash equilibrium, is a state where everybody is playing their best response. Right. So if you think about the situation, suppose we fix the action of all the players, and suppose that under this current decision, everybody is playing their optimal strategies. This means that if they switch to another strategy, it would lead to potentially a worse payoff. It would never lead to a better payoff, right? Then this means that there is no incentive for any player to deviate from their current choice, right? So this means that, well, right now we have a sort of a locking situation where everybody is just playing their optimal decision. They can, in that sense, they cannot change the state of the game anymore, so they actually reach stability. And that stability is what we call the Nash Equilibrium. Okay. So let's look at this situation when we have two firms, and each of them has three options, A, B, C. So you can think of them as representing three clients. If the two firms approach the same client, then the client will give half its business to each of them, right? And firm one is too small to attract business on its own, so it has to attract business together with firm two. But if firm two approaches B and C on its own, then it will get the full business from B and C. And A only want to do business if both firms approach A. Right. So in this case, we can construct this matrix, which represents the situation. You can simply analyze strictly dominant strategy, and you can find that there's no strictly dominant strategy of either player. And if you apply the iterative elimination algorithm, you may find that, in fact, you cannot eliminate any strategy because there's no strategy that is dominated. Right. So what can we do? Well, now we want to analyze whether there is a Nash equilibrium. How do we do that? Well, to compute the pure strategy Nash equilibrium in a two-player game, what we do is we analyze for each player their best response to other players, to the other players' strategies. Suppose that firm 2 chooses A. Then in this case, the best response for firm 1 will be to choose A. Suppose firm 2 chooses B, then the best response for firm 1 will be to choose B. And similarly, if firm 2 chooses C, then the best response for firm 1 is to choose C as well. Right? So this means essentially we need to identify entries in this matrix that are seen to be the optimal response from the point of view of firm 1. And we call these entries Y1. Right? So these are all of the strategy profiles that represents best responses for player 1. And then if you look at from the point of view of player 2, if player 1 chooses A, then firm 2's best response will be A as well. If firm 1 chooses B, then firm 2 would choose C. If firm 1 chooses C, then firm 2 would choose B. Right? So now we have this entry, and this entry. So that's also another collection of strategy profiles in the game that correspond to player 2's optimal response, the best response. Right? But what we want to find out is the situation where both player 1 and player 2 are playing their optimal response to each other's pure strategies, and that essentially asks for the intersection of Y1 and Y2, and that will be the containing all the Nash equilibria in this game. Right? So visually, we can represent the Y1 set using underline, the blue underlines at each column. Remember, for each column, we will need to select the best response for player 1. So this will be this one, and this one. And then we can indicate the second set Y2 using the overlines, the red overlines, for every row. For every row, we want to select the best response for player 2. This will be this one, and this one. And what is the Nash equilibrium? It will be a strategy profile that has both underline and overline, and that will be, there's only one such strategy profile, which is A and A, right? So in this game, there's a unique pure strategy Nash equilibrium, A and A. We now look at a slightly more complex situation which involves more than two players. So suppose there are n firms, so they're just factories, and they make their productions. But as part of their production, they need to consume a certain amount of clean air. So this clean air, it doesn't have to be clean air. It could be just some sort of natural resources. And there's a total amount of natural resources. So the natural resources is not unlimited, right? But this means that each firm will need to choose a level of consumption of the natural resource between 0 and the maximum level, so 0 and K. Right. So given the strategy profile S1, S2 up to Sn, we want to determine the payoff to each agent. So for the ice factory, what's the payoff? The payoff consists of two parts. Of course, the more resources that the factory consumes, the better the payoff. So there's a first component which relies on the consumption of the first firm, and there's a second term which represent what we call the externality, and so that's the remaining natural resources, like clean air, that's left, and these are not just taken by the ice factory, but taken by all the factories, and therefore we're interested in the difference between K and the sum of all of the SJs, right? And just like in the first term, we also take log. So we take log of both of these, and that's going to be the payoff for the ice player. And of course, this is for every player. So now, if you think about it, we have a finite number of players, but the action of each of the players is no longer a finite set. It's no longer a discrete set, because it can be any level, so a real number between the range of 0 and K. Right. So in this case, it's very difficult. Well, we cannot represent this game as a matrix, but we still want to calculate Nash equilibrium for this case. How do we do that? We employ some calculus. So what is the best response of the player? We need to solve the equation. So we take the derivative of SI with respect to Fi with respect to SI. So. And this would give us this, and we set this to be 0. So we want to look for the SI which satisfies this equation. So that will be this one. So suppose n is just equal to 2, then the best response to the players are S1 equals to K minus S2 divided by 2, and S2 equals to K minus S1 divided by 2. And you can see that if it solves this set of equations, you get S1 and S2 to be equal to K divided by 3. So in the Nash equilibrium, when the players, and suppose there are only two factories that are competing, then the player will play the best response to each other at the level of K divided by 3. Right. So that is the Nash equilibrium, but now the question is this strategy profile socially optimal? So is this really socially desirable outcome? Let's think about it. The social welfare that we are interested in will be the summed payoff of both of the players. That would be twice, well, actually adding the log of SI plus the log of K minus S1 plus S2. So we add this for both of the players, and using again some mathematical some simple calculus, we can compute that the maximum value for this social welfare will be that both players playing at the level K divided by 4. Right. So it means that both factories, if they're playing their optimal about their best response to each other. So in this Nash equilibrium, they are consuming more resources than they would if they're in a socially optimal manner. Right? So it's k divided by 3 versus k divided by 4. Right? The conclusion, though, that at the end of the day, the morale of the story would be, the moral of the story would be to give people the freedom to make choices, may make them all worse off than if those choices were somehow regulated. So we need some regulation. So let's summarize what we just described. We have the properties of Nash equilibrium. So first of all, if a strategy is either an SDSE or an IEE, then the strategy profile is the unique Nash equilibrium. Repeat. So now let's summarize the property of Nash equilibria. We can quite easily prove that if a strategy profile is either an SDSE or the unique iterative elimination equilibrium, then this strategy profile is the only Nash equilibrium of the game. Right? However, there are cases where pure strategy Nash equilibrium may not exist. And in the next lecture, we're going to look at another form of Nash equilibrium, namely the mixed strategy Nash equilibria, and that always exists. Right? Also, we can conclude that Nash equilibrium may not be unique because in some cases you can have multiple Nash equilibria. And according to the last example, we can see that Nash equilibrium may not be socially desirable, so may not be Pareto optimal. Right, so these are the properties that we can conclude about Nash equilibria. As a summary of this lecture, we've introduced static games. So we look at normal form games, and we just look at the simplest model where the agent has perfect information, that everything is known. And we, like what I said, I mean, that this is the beginning of a theoretical foundation to model agent behavior and to make prediction of agent behavior in a multi-agent system. Although right now, if we just focus on this very simple static game scenario, it still seems to be quite preliminary. And what is a solution concept in the game? We've defined a number of solution concepts, namely strict dominating strategy equilibrium, iterative elimination equilibrium, and Nash equilibrium. What are the correlation among these solution concepts? What does Pareto optimality mean? And how do we compute these equilibria, right? So in particular, how do we compute pure strategy Nash equilibrium for a two-player game? And that's the end of this lecture, and I'll see you in the next lecture.